Good afternoon, good evening. April 2nd, 2023. I thought we might look at some of these books that have to do with the differential. The differential, that where it's on solutions are as of the function itself, or those being differential equations, or the differential as the differential analysis that the integral calculus is determining as of rise of over run of the tangent to a curve. What is the curve's instantaneous change with respect to another quantity, as with regards to usually time, and being the most usual notion of the names of the higher order derivatives of being velocity, acceleration, and higher order acceleration, snap, crackle, pop, or a jerk, and this kind of thing, that result then the integration is its inverse operation, and integration is the act of mensuration, which results in quadrature, the computing of the area, as of the methods of exhaustion after Archimedes and Eudoxus, what result as the how you say computation of area in beyond just the methods of finite differences. And there's much to be said for various methods of finite differences, and particularly in as regards to when they offer closed form solutions in finitely many terms for suitable possible areas of integration by means of methods of finite differences, that the differential calculus offers again in the milieu of real analysis, where we have the differential calculus and its complement, the integral calculus. The differential calculus and the integral calculus offer beyond means of finite differences a means of infinitesimal differences. It's what we usually call the differential. Thus, that when we speak of the differential, it usually refers to, as per Leibniz and the invention of the methods of the integral calculus, most familiar from the time of Newton and Leibniz, that the differential is written as d, d for differential, and it reflects the variable or the coordinate in terms of which the summation or the integration after our formalization, that it's very carefully pieced back together, a summation as of Riemann or Lebesgue, that for Stieltjes, that these sorts of integration occur according to the analytical character, which describes the area of vanishing amounts of coordinated areas that result, making for a means that goes beyond the methods of finite differences, perfect values after the definition of limit, or in our standard way, that is all entirely formalized and driven completely by rules from the very beginning, for a very standard contrivances, the methods of finite differences. Then there's that for some particular solutions of integral equations and differential equations. There are those where the solutions are framed in terms of that the solution to the equation is as of the derivative or the integral, respectively, of the equation itself. And these are what we call differential equations. So I haven't much studied differential equations. Now, when I studied differential equations, we had some initial exposure to it in like calc in high school. But usually just as in the course of that, the exponent is its own antiderivative and this kind of thing. And that the rules for the definition of what is the derivative of the exponential function is carrying down the constant of the variable in its term, and the exponent's operand, and out as a constant in front, and that results the function that is the derivative to be evaluated by plugging in a point, and as what results is its value of the function, its derivative, at a given point in its domain, the derivative, its value, the slope of the tangent curve to the function at that point, is computed after a rise over run, and the parametric slope of a line, y equals mx plus b, where that's a parametric form for a line, vis-a-vis what is parametric forms for planes and this kind of thing that kind of arise in usual discussions of linear analysis. So then at some point in time, there's discussions of things like the radiation of heat, where some of the earliest discoverers of formulas that have these forms were kind of like the Bernoulli brothers, Jacob Bernoulli and his brother, and then there's Fourier, Joseph Fourier, or as it is, he discovered some of the basic equations that govern the radiation in time of heat, and that it's as of about a quadratic or the inverse square and some of these kinds of solutions, that in terms of the analysis, that it's the differential equations and differential functions which make for these to be so. So then we have differential equations, then ordinary differential equations, and if I don't recall incorrectly, and again, any mistakes are my own, and not to be from being led astray or anything, it's just my errors. The ordinary differential equations are those that have linear solutions. And when we get into the solutions of differential equations, then there's some things to do with terms that there's the exact, and then there's the stationary, and there's some properties of these functions that result they're so what we call well-behaved, so that then, given that there are various initial values and boundary values, that when we get into discussion after solutions in terms of functions that are families of solutions or families of equations that may all solve differential equations, then we're left often to look for real valued variables that have solutions in these equations, and then B, solutions to these equations with respect to the parametrics or the implicits, which result that after our methods, which have arisen and been employed in various ways for the solution of differential equations, that it's possible to arrive at those principal solutions that also happen to be real numbers, and thus that reflect what would be according to, if the mechanism, when we ascribe these differential models of mathematics to differential models in physics, if they so apply that the models are accurate and the mechanism is so, then we can talk about how those are predictive values or predicted values, and why the study of differential equations is so relevant and paramount to all these types of applications. So I have here some books, and I imagine I might just leaf through them a bit, and they talk about the differential equations, solution using symmetries, and then there's this, that's a history of the circle, differential topology and quantum field theory. And then this was where here's this differential geometry, curved surfaces and manifolds. And then there was something else here that I thought was apropos. It's contributions to nonlinear partial differential equations. And this is a collection of symposium or something like that. This one is about potential theory, probability theory. This being just a usual collection of things. And here's a book, Theory of Thermally Induced Gas Phase Reactions. And it wouldn't be too surprising to find that its functions are in terms of the exponent. We talk about the equilibrium rate and partition functions. Oftentimes we'll talk about methods of variation and what goes into means of establishing what are solutions, and then what are numerical methods to approximate these solutions according to where it's possible to establish beyond what systems of solutions are well behaved for initial values and boundary values for what are called IVP, initial value problems, and BVP, boundary value problems, that the numerical methods which are employed to arrive at crunching out the numbers also have their formalisms satisfied to make for good solutions. That, for example, this book that discusses a qualitative study of the mechanism of vibrational excitation of diatomic molecules in the quantum mechanical, and about the parameters and the dimensions and dimensionless, and his discussion of the Morse potential. And that then this gets into equilibria and non-equilibria, and in terms of our dynamical modeling. There's that the differential equations arise in many modeled systems of dynamical modeling as what reflect frameworks for establishing their forms. And here the author mentions Benson and Fueno, and also Bunker, had derived for the expression Rm bracket cubed on the order of t to the negative cubed. Here is the inverse cube is the milieu for the temperature dependence of Rm. In addition, it is suggested that the increase in the number of collisions Z with increasing temperature is largely compensated by a decrease in the effective collision cross-section of A, B, and M. So these are the ideas that some things are compensatory, or that there's regulation in an equilibrium, that certain values, according to the ergodic in their Markov models, in Markov processes, which is a pretty general way to establish how something behaves as a value over time, have that they'll reach a non-zero equilibrium. This is sometimes also called in the dynamical modeling the predator-prey modeling, which is along the lines of that the wolves eat the sheep until there's either enough sheep left over, or that there's not so many wolves, so they don't eat all the sheep, until there's such time as there's reached an equilibrium, or one of the other populations crash, and then both populations crash. Or there's that the wolf population crashes and the sheep population explodes, leading to the opportunity for a wolf to have a runaway process, is what results that the predator-prey equilibrium is after these dynamical systems of modeling. An example from dynamical modeling in other epidemiological models that are used, for example, in terms of like models of disease transmission, or models of many other economic systems, that they have equilibrium in the dynamical modeling, which results that it has an oscillation effect, as it is, where in a lot of the solutions of the nonlinear equations we've been talking about reading Mogan's book, is that there's the oscillating, the restitutive tendency and the oscillating property, as there is the dissipating tendency and the attenuating property, or the vice versa. These tendencies and properties is that in some models, what you would see is that the oscillation is primary. And in other models, you'd see what the restitution is primary, whether it flips side to side or is flipped side to side, whether it goes out or out it goes. Reading that these are ways to assign, without much further ado, a method in the naming of the things. And it's kind of like they say sometimes in software engineering. Software engineering is just the art of giving things appropriate descriptive names and then enforcing the behavior according to well-defined behavior, so you don't have undefined behavior. But it's really all about those names. That the restitutive and the oscillating here, and the attenuative after the dissipating here, is for this restitutive and dissipating, that then the oscillating and attenuative work out that in these, for example, of predator-prey models, which end up having linear parameters in simple terms after the solutions, they have these as of solved by these systems of differential equations for dynamical modeling. And this is a way that so results that then you can give somebody a card out to the field and say, go measure how many of these sheep you find each year, or something like that. But then they can use that, plug that back into the models, and get an idea of what that means for estimates and predictions, what then get into our statistical methods and after our scientific methods, so that then we can come across usual definitions of the entertainment of a statistical hypotheses, and whether according to the statistical method we can validate or invalidate the null hypothesis of what's a well-framed statistical setting and what is a well-controlled statistical experiment, which results a statistically sound hypothetical invalidation or lack thereof. Just like in our scientific method, we only have falsification. In our statistical method, we only have invalidation of the null hypothesis. So that then it's for these means where we get exact solutions, and again, exact is a specific term for the ordinary differential equations in their analysis, that these are the kinds of things that go into a lot of the kind of setup that everybody should know if they want to be a scientist and a statistician and a mathematician and this kind of thing in the applied. Besides is for the pure mathematics and general knowledge of according to vocabulary and natural language, that every word so selected for the vocabulary and the common terms has a well understood association and a direct connection to its definitions formally. So this is a pretty great book, actually. This Theory of Thermally Induced Gas Phase Reactions, as it gets into various considerations of the kinematic and the kinetic and the energy in the systems with regards to the fundamentally stochastic behavior of particles, yet that they live inside given manifolds, and this kind of thing. So again, these books are pretty high level and reflected terms. And getting into them a bit is where I've looked to this differential equations, their solutions using symmetries, as what may be an example of something that for somebody who's had a course in ODEs and an introduction to nonlinear ODEs, and as it were, or ODEs that in particular parameterizations of nonlinear systems have ODEs. That this book from Cambridge University Press by Hans Stefani in the Section Physik Friedrich Schiller Universität in Jena, Deutsch DR, Malcolm McCallum, School of Mathematical Sciences, Queen Mary College in London, 1989, has that the table of contents talks about symmetries. So this book is about the algebraic approaches to these things. Reading out solutions of linear equations, there's a lot to be said for methods of linear analysis. And so linear algebra and the notions of the determinant, and then the notions of echelon form, and the notions of solutions of linear systems of linear equations make for that sometimes these problems are posed as what results eventually that then they're framed in terms of linear equations with respect to each other. Thus that in a given number of x independent variables, if there's x linear equations that define it so that you can end up reducing the echelon form of the matrix so that each one of the variables can be defined in terms of a constant, or that otherwise ends up being reformulated or parameterized or implicit about these other variables, that then in this system of linear equations it's possible to arrive at numbers that solve each of the, or ranges of numbers that solve each of these of the system of equations. Thus that you can say that there are solutions to the system of equations. Then that there's other tests or indicators of the values that come out of these solutions of those systems of equations that are characteristic of the functions under analysis, that it's possible to arrive at those sometimes, or when possible, that they are putatively solutions for these equations in real values, or with sensical values for these things. So this approach then is a high-level approach after that in terms of symmetries and the use of where this algebra is to be carried out and beyond, for example, when it's something that you can reduce to a system of linear equations in this manner, and then use algebra of a sort, that there's all kinds of objects of mathematics that we call having algebras. And the most familiar are the numbers, because we have first our operations on the numbers. We would call them, say, operators before we would say they're in an algebra. And it's arguable whether or not that the results of abstract algebra called the group, which has an identity and inverses and all its members are in the group and that's closed, the operation is called an algebra. And that then there's for like the field, that it has the additive and multiplicative identities and ends up showing that the distributive, associative, and commutative laws of arithmetic are carried out in it. That otherwise the objects of arithmetic, the numbers we would usually call them, that have addition and subtraction, there its inverse, and multiplication and division, its inverse, that those numbers and values can as well be seen to have that the objects have, that is proved that their operations are closed, instead of that, as for the algebra's group, that the operations closure proves that the elements exist and that the operations are fulfilled either way. So when we look at arithmetic and algebra and call them the same thing, that they admit all the same solutions, it's true, and that's a fair abstraction, and it's mathematics, but there's also a mathematics where that's to be made explicit what was made implicit, that extensionality equals of their intentionality equals, and there's no other things that equals. That is to say, arithmetic and algebra are separate, and when they're commingled, then it results that is its own thing. And then with regards to systems that consider extensions to the changes of arithmetic or algebra, either way, that involve having addendums to the space, like a point at infinity, or making for the modular that there's an unusual topology, or after the digital, these being somewhat contrivances, where we might define arithmetic as addition only and division only, and then just that subtraction and multiplication work out as this kind of funny thing that we end up having to do long subtraction or something like that, that makes it so that what is otherwise modeled by an arithmetic continuum is modeled by this reformulated, or rather restated, collection of operations that establish an operator calculus, that establish induction over the cases of the elements of things. That is just the point that arithmetic and algebra are not necessarily the same. Now here in this book about the solutions by symmetries of systems of differential equations, is that we are already working in this realm where we have, after the fundamental theorems of calculus and the fundamental theorems of derivative and this kind of thing, about how we've established what are some of the fundamental solutions to the differential equations in terms of their differentials, and integrating those or differentiating those and resulting these equations, and with their constants and so on, that are implicits after their functions under analysis, and in ranges of analysis you result their functions as analyzed, and the implicits or conditions of that. So this method of solutions of symmetries basically is able to add another algebra on top of this other algebra. Just like there was a discussion briefly ago about the difference between arithmetic and algebra, and the ways to consider that differences in arithmetic, or some degenerate arithmetic, or some restated arithmetic, that is still equivalent, that it's isomorphic in the space of all the operator calculus of it, or not, about where it's held in and where it's let out, that this extra algebra of means of symmetries is held up over the usual methods of this differential analysis of regular functions, that then it's possible, when it's so bounded and framed together and held under the relevant conditions, that it opens a new field of methods for the applied that make it possible, particularly for something like dynamical systems, that have that the analysis is often original with the attractors and repellers of what they call chaos theory, which is called dynamical systems or dynamical modeling. That these kinds of methods end up being from what's the general applied of differential analysis, and then what gets into the example of the finite differences, and that there's methods of finite differences, numerical methods that in their realm, given some constraints, are perfect and much, much more direct, close, and great. That this offers up above what is otherwise perfectly suitable for all the applied of any real functions, given some particular other factors, the ability to make our red and green sheep, as it were, from the discussion of the contrivances, to result that this is a thing, and it's so formalizable, so that we can maintain rigor and get sensible values out of these things, while yet keeping things quite regular. So, and I haven't read this book, and the example from reading Mulgan's book, it can take quite a while to read a mathematical work, but looking at his table of contents, I'll just read off some of the touchstones of its table of contents. One is ordinary differential equations. Chapter 2 is partial differential equations. And so the partial is just a section of the differential equation, usually written in Greek little d or d, that is holding the other variables constant. So it's basically when you're taking the derivative of a given surface, you draw the coordinates as projected at that point, and then only consider the slope in that one direction, where that might not be the same as the slope in the other directions, as from a global minimum or global maximum, where it has a cusp of regular curvature at it, where they would be the same. That's the idea of these methods of symmetries, that they would be the same, so that you can work around them, as it were, that otherwise the methods of partial differential equation are scribed out the way it is one. And that way, when you're doing the algebraic manipulation of the variables and the transformation of the terms and all that kind of stuff, you can bring out everything else as constant, or for example, cancel it. So that's the idea of what would be a use for some of these methods of using symmetries, is that then you're able to treat some of these systems in the dynamical modeling, where dynamical modeling is basically the entire abstract thing up above real analysis, which is the entire abstract thing of application of computing things given real numbered formulas and real numbered variables in real functions and non-standard real functions that have real valued variables. This is an example of this kind of thing. So ordinary differential equations, point transformations and their generators. The generator is a concept that describes a sequence that so results from a given mathematical thing that kind of tents out or stakes out in terms of some kind of outer and inner product, or here what results as a series of indicated terms. What is a generator? And so he talks about one parameter groups of point transformations and their infinitesimal generators. The infinitesimal, of course, is not part of our standard real analysis, but it's a totally intuitive thing, which means an instantaneous rate of change, or it means an arbitrarily small thing. And so that here, when he's describing something like that, when we were talking about a cusp of constant curvature and the derivative or gradient as about it being a local minimum or maximum with respect to variable, e.g. time or position, that this is an example of then this method of variations, and the variational principle is establishing for this kind of preliminary what that kind of thing is. And again, I'm reading quite a lot into that natural language description framed in these technical terms, but that's what it is. And it's as so far as that's held up and altogether carried out, that what makes it providing attractability. And for something along the lines of sensibility, tractability, and fungibility, or sensibility, fungibility, and tractability as being usual guiding principles of what you can make use of a tool set or toolkit of equations or formulas or methods that results as sensible, fungible, and tractable. Then he goes on to, in just reading off these systems, the sections of this chapter 1, transformation laws, one-point parameter groups of point transformations that are infinitesimal generators. Groups is the simplest kind of algebra that people are usually familiar with. That's the one with the identity and then the whether or not it has a commutative law, or whether or not it's called the property of being abelian, and it's closed, and there's inverses. And then transformation laws and normal forms of generators. And the normal form is what happens when there are any of a given number of contrived forms, that there's a particular kind of normal form that you can rewrite these ones that have equivalent representations in the equivalence class of the forms, that they have an unambiguous normative normal form. Extensions of transformations and their generators. Multiple parameter groups of transformations and their generators. So here it looks that before we begin to read this chapter 1, the section, that he's talking about algebra's most usual simple tool, the group, for group theory. What is the group of all groups? It's a group. But what's its operation is the question. And the description of for what's an infinitesimal generator, and it'll be interesting to see what formalism he offers for that, or if it's just as for a framework of delta epsilon x as building out and about how it's so that later on it'll be implicit throughout. For laws about these things and making a calculus of them and an operator framework for them and an algebra of them, will then describe what are the usual algebraic properties like commutativity, transitivity, distributivity when there are multiple operations in algebra, and lack thereof, or they're anti-commutativity, anti-associativity, anti-transitivity. So that was what section 2 looks like, chapter 1, and then section 3 is about Lie symmetries. So Lie is Sophus Lie was, and his name is spelled L-I-E, it's spelled like lie, pronounced Lie. That Sophus Lie, if I recall correctly, was a Swede, and he invented lots of methods of Lie groups and Lie symmetries. So when you hear about physics and Lie symmetries and this and that you'll find that it's very regularly held up. So he defines or describes in this section Lie point symmetries of ODEs, ordinary differential equations, the basic definitions and properties. So maybe that'd be a good place to start. So looking through here, he says, the preface reads from this would be from Stephanie or Stefani, respective as what it is, or if that's correct, and McCallum. Several years ago, when reading an old paper on a special class of solutions to Einstein's field equations, I became aware by pure chance of the existence of Lie's method of integrating ordinary differential equations when their symmetries are known. Since I had never heard of or read about this method, I consulted friends and textbooks to make sure that this was not only my personal fault and ignorance. Lie invented the theory of Lie groups when studying symmetries of differential equations. So, Lie groups became well known, but their original field of fruitful application remained hidden in the literature and either did not get into textbooks, or if it did, only appeared in very mutilated versions. This is where if you do a lot of the research on dynamical methods in terms of like epidemiological and studies of dynamical methods, and especially like studies of natural settings, you'll find all sorts, these usual grab bag methods being applied, because besides the bulk, the bolus, as it were, of all the linear curriculum, that's all printed out and made available for everybody, then after you get through an undergraduate in curriculum in mathematics, then there's basically all these branches that this is an example of a kind of thing for dynamical methods that could form a course in dynamical methods that would be very integral and part of its basic toolkit, that for others is part of the extended toolkit. And to hear about its history and historiography, it's about like when there are 14th century proofs of column circumferences gathering dust in Hilbert's Infinite Living Museum of Mathematics. They're still good, if dusty. They're still sharp, if rusty. But then it goes, here the author is describing that he felt that these were underserved. Lie groups became well known, and in fact they're very, very useful in the days, but their original field of fruitful application remained hidden in the literature and either did not get into textbooks or if it did, only appeared in very mutilated versions. Hence, many people who could have profited from this method simply were not aware of its existence. Even of the monographs then available, most contain only part of what I found when reading Lie's original papers, which fortunately enough were written in his native language. With the eagerness of a freshly baptized believer, I therefore decided to give a series of lectures on the subject, lectures that eventually developed into this book. This book is intended to be an introduction. Almost nothing written in it is my own, but it is rather difficult to give proper credit to the origins of the various ideas and results, not only because of the gaps in my memory, but also because most of the material presented here is due to Lie, with only minor improvements and generalizations by later workers who rediscovered and used Lie's results. His footnote reads, many remarks on the historical development of the subject can be found in Olver's, O-L-V-E-R, Olver's textbook. This book could not have been written without the help and advice given me in many discussions, Dietrich Kramer, Malcolm McCallum, and Gernot Negebauer, and it has been English. Thanks for our Catholic. All right. So in the introduction, as we were reading the table of contents before, I'm getting into a bit. Suppose you have to solve an ordinary differential equation of, say, second order. For example, y prime prime, the d squared y dx, or the second order derivative of y, equals quantity x minus y prime cubed, and that y prime equals dy dx, or is on the order of, rather. That he's describing a differential equation, so its derivative is defined in terms of the equation itself and in other variables. Or y to the n equals x and y squared. How can you proceed? First, you will certainly check whether the differential equation belongs to a class you know how to treat, for preference to the class of linear differential equations, or whether it can be transformed into a member of such a class by simple transformations of the dependent and independent variables. If unsuccessful, you may look up a textbook or a collection of solutions, and if that does not help and the problem is of some importance, you will try more elaborate transformation methods and ad hoc ansatze. Ansatze are kind of like Gedanke, they're setups, to find the solution. But it sometimes may and will happen that you have to leave the problem unsolved with the uneasy feeling that there might be a method you have overlooked or you are unaware of, and the question of whether a solution to your differential equation can be given in terms of some elementary simple functions will still be open. For the differential givens above, the answer to that question will be given in sections 5.2 and 7.5. So it appears that he's describing that these solutions that are third order in the one, and that its higher order derivatives are of that form, where it's rather interesting that all the higher order derivatives are defined in the same form, that they're given in this book as examples. For a partial differential equation such as u comma xx u comma yy minus u squared comma xy minus 1 equals 0, and this is similar to the notation as we've been reading in Mogan's book on nonlinear mechanical effects and applications, that u and xx and u and yy minus u squared xy minus 1 equals 0, that you'd often think to factor that, like ux plus 1, ux minus 1. The situation is similar, although the specific questions are different. Since really powerful methods to deal with PDEs of second order are easily available only for linear equations, you may first try to transform the given differential equation into a linear one, for the example, If unsuccessful, you may perhaps set out to find as many special solutions as possible by using standard techniques such as separation of variables, writing u as a product of sum of functions of different variables, or reduction of variables, assuming that u depends on less independent variables. But again, the question remains open whether these methods will work and whether there are other methods that may prove useful. So here, this just kind of goes on to describe, kind of as I mentioned, that there's quite a zoo. That there are many mathematical methods that are kind of pulled together in a grab bag toolkit, assortment that are used for solving differential equations. And this gets into things like, well, why is the three-body problem so hard to solve? Of their orbits or their gravitational attraction? It's a big differential system, and according to arbitrary initial conditions, it ends up being arbitrarily contrived how to solve them. And similarly with that was like, well, we need to frame it in terms of orbits and frame it in terms of symmetries if we're going to have a chance at all to solve them for some of these alternate things, or at least to close the box the other way and then just sweep in the corner all that's left of the truly what they call pathological or hysteretic, widely varying solutions of these systems of equations. So the author here just kind of reminds that systems of PDEs or system of ODEs have a bunch of different things that go into the preliminaries to define and well define what their setting is, so that it results then it's possible to pull out all sorts of tools from the grab bag toolkit assortment of methods that makes it possible to usually pick the one that's most well known, the solutions, and then also to arrive at various contrived solutions, or as he calls it, the ansatz. In both cases, for ordinary and for partial differential equations, the unmistakable answers to all these questions is that in the majority of the cases where exact solutions of a differential can be found, the underlying property is a symmetry of that equation. Moreover, there are practical methods to find these symmetries if they exist and use them in solving the differential equation. So most of our tools are built up from our standard real analysis and our fundamental theorems of the integral calculus and the calculus. And that is what's used for all our univariate calculus, and it's used for our vector calculus, and it's used for our advanced calculus, and it's used for all this stuff. So this is just describing that in the same sense of notation that it gets a little crowded, but at the same time, it's a common setting. So here, and he's describing that it's so that for these things in that setting, that again, there's a lot to be said for symmetry laws, because that defines the commutativity of sorts about it. Excuse me, that's just commutativity. It defines a commutativity about it of sorts. It defines an associativity about it of sorts. It finds beyond if it oscillates in the recitative, if it dissipates or is attenuative. It defines the transitivity about that of sorts. So those are the kinds of options in terms of what are called the inverse and the reciprocal, in terms of inner and outer products, in terms of the scalar space, points in space, or a basis and a vector space. So this book, back to the author, this book is devoted to the study of symmetries of differential equations with the emphasis on how to use symmetries to find solutions. The typical way to define and find a symmetry is to first characterize a class of admitted transformations of variables and look for special transformations in this class that leave a given differential equation invariant, meaning what's left can be dropped as a constant, according to the algebra, that in then the usual acts of fundamental differentiation and integration or what, that constants drop out. The more general the admissible transformations are, the more symmetries will exist, but the more difficult it will be to find them and to exploit them to give an integration procedure. I have therefore arranged the material according to the generality of the allowed transformations, beginning with lead point transformations and symmetries and ending with generalized dynamical and Lebesgue symmetries. Some aspects of the theory could have been treated simultaneously for ordinary and for partial differential equations. To make the book easier to read, the subject has been divided. That some paragraphs in the second part on PDEs are in essence slightly generalized repetitions of what has already been said in the first part in the context of ODEs. Although that does not apply, the second part is completely self-contained. One can start reading there if interested only in PDEs or at the price of meeting a comparatively concise presentation from the very beginning. The book is written in an intuitive fashion. None of the proofs is really watertight, in that the necessary assumptions are not clearly stated, e.g. most of the functions that appear are tacitly assumed to be differentiable or even analytic. The emphasis is always on presenting the main ideas and giving advice on how to use them in practice. Most of the material is standard and long known. No references are given, therefore, in the text, but a small guide to the existing literature is added as an appendix. So by limiting his discussion to systems equations that are real functions, first of all, so that all the tools of the usual toolkit and assortment are readily available, the author is able to build on that platform. And then as he gets into what is going to be his methods about the Lie algebras and Lie groups and symmetries, Lie symmetries, and how those are going to be used later on in these solutions, that hopefully this will be a pretty regular form to what would then probably be the way it's done 30 years later all throughout the curriculum, if with some slightly different names or ordering. Now so we're going to look at that some more later. Now this differential geometry, and if we look at it for a bit here, has that differential geometry requires standard calculus, including several variables, and linear algebra. And only later there's some familiarity with complex function theory. And describes the computer algebra system, Maple, is used. Wolfram's Mathematica and Maple, and those two are were at one point the premier settings for computer algebra systems, which is where those can be considered calculators or plug-in equations and it gives solutions or these kinds of things, where whether Mathematica or Maple was considered of providing the most solutions. At least one point in time, it was Maple or Maple 5, the V for the letter 5, Roman letter 5, Maplev. That at one point in time, Maplev was the best mathematician in the world. And that's a joke, but Maple is a language as well. And then this book is written in LaTeX, where Tech is Donald Knuth's typesetting system. And besides PostScript plain, Tech is the input format for most all mathematics books printed ever, in the sense that if you don't include Euclid's geometry and such things from antiquity and typesetting, that if you think of everything that's since the 70s and 80s and 90s, almost all of it is written in Tech, which is written T-E-X, Tech. And then Leslie Lamport's LaTeX is very widely used. It's a setting of macros for Tech. This is when you want to write an article like an AMS article document, which has all the settings made that make it print ready for submitting a proof to a publisher, that it is the correct style for any of these forms. It also has the most well-known and widely used setting for the formatting of mathematical formulas in text and typesetting. And then it results that it's written in printer language or PostScript or something like that. Though that, for the most part, all mathematicians who write papers for it do it in Tech. So, notations and prerequisites from analysis. He talks about Euclidean differential geometry. And so when we say differential geometry, in addition, we use a topological structure in the form of limits, open sets, differentiation, and integration. So these are kind of his requirements, and once given them, then all the rest, his theorems will kind of be defined on those. By fixing a preferred point as the origin, one can identify Euclidean space e to the n with r to the n, which will be done implicitly in this book. So in that sense, the orthonormal vector basis of the space of the real numbers in their Cartesian product in n dimensions, it's called r to the n, or rn. And thus that r squared is the plane, and r cubed is the volume. And then the higher order terms are called hypervolumes. It's usual for things that have planar representations like circles and spheres, and then rest is hyperspheres. They have squares and cubes. The rest are hypercubes. There's still, though, that there are various names for those higher order things, like the tesseract, the higher order cube, and this kind of thing. And here it's in R cubed or R3, so it's very familiar in a usual setting, and a lot of other things that would be very involved are kind of assumed. R3 is Rn is a vector space with an inner product. He talks about inner and outer products. Talk about the metric. Talk about the norm. Talk about the inner product. Symmetry by linearity. Positive definiteness. Positive definiteness is when two vectors have a non-zero inner product. And that positive definite is used as an adjective that describes a property to an equation or a system later that will be relevant when results are developed that hold so necessarily only when the property holds, where they might or might not hold when the property doesn't hold, but otherwise that would be a negative property that is only so holds when the negative property holds. These are the kinds of things that get into our definitions. And we talk about the length of a vector. It's written as in two brackets, or two pipes is the notation for length. And it's root of the scalar product, or inner product. And the angle is introduced in terms of cosine of the inner products and their lengths and the dot products of their lengths. So then we have Rn as a topological space, and then he says he's picking a topology of real numbers. The real numbers, I mean, any number of topologies, any given association of the elements within it and the subsets within it that fulfills being a topology could be a topology, and that it has one at all is a topological space. And then how you assign and ascribe values to its points and neighborhoods is how you say a topology is defined. The topology of Rn is defined as the system of all open sets. So this is called an open topology. It's very usual, and it basically leaves other issues with regard to topology theory out. All right. Differentiation in Rn. The most important notion for the contents of this book, which is also the source of the name differential geometry, is that of derivative or differentiation of real value functions which are defined on some open set U subset Rn, or more generally of maps defined on open sets U subset Rn to Rm. To say that a function is differentiable is to say that it can be linearized up to terms of second order. More precisely, a map F that is U maps to Rm is said to be differentiable at a point x in U if there's a linear map Ax that from Rn into Rm such that in a neighborhood U, big U, epsilon of x, or the infinitesimal neighborhood about x, that neighborhood of x, one has fx plus epsilon equals fx plus ax epsilon plus the error term, or what, of the length of epsilon. Here the symbol O of the length of epsilon means that the terms indicated by it tend to 0 as epsilon goes to 0 even after previous division by epsilon. Yes, there is division by 0 if you have it included here, and that's an issue. Then A sub x is the linear map described by the Jacobi matrix, or the Jacobian of f, that J sub x f equals the sum of partials, or their containment over x of partial of fi with respect to xj, I comma j. The rank of the map f at the point x is then defined as the rank of the Jacobian. For our purposes, the most important case is the one in which f is differentiable at every point x and u, and the rank is everywhere maximal. In this case, one calls the map f an immersion, in case n less than or equal to m, or submersion, in case n greater than or equal to m. An immersion, respectively submersion, is characterized by the fact that the Jacobian represents an injective, respectively surjective linear mapping, the linearization of f. The importance of this property becomes quite clear in the implicit function theorem. So differential geometry is a lot like when we talk about continuous functions, and then we have various classes of continuous functions that are differentiable, differentiable, and differentiable in a sense, and that CFD functions are infinitely differentiable. And so it seems here that it's similar with differential geometry, and otherwise that it's really as after the existence of what is an analog to what's a continuous function, then instead these linearizations or immersions or submersions are defined, which are a complementary concept to continuous functions in the usual standard analysis with the usual definition of a continuous function. That this differential geometry is basic fundamental is it's a different toolkit. It's a toolkit for a different set of tools, and it will so happen that some of those will be interchangeable, but only in a particular bridge results, or how things have their intentionality and extensionality and admit algebras that work on the same objects of different forms. So here, that's interesting. I didn't really know that yet so much about differential geometry. So we looked a little bit at differential equations and differential geometry, and then there's differential topology to consider for a second, where differential equations is all about the space of continuous functions. So differential topology and quantum field theory is from Academic Press by Charles Nash of St. Patrick's College, Maynooth, Ireland, from 1991. Preface reads, the 20th century has been witness to a great burgeoning of mathematics and physics. In the early part of the century, the new physical theories of relativity and quantum mechanics made extensive use of the machinery of differential geometry and Hilbert spaces. Sometime later, quantum field theory began to pose difficult mathematical problems. As a partial response to this, the subject of axiomatic quantum field theory was born. The main thrust of this approach was to tackle the formidable problems of quantum field theory head-on using the most powerful mathematical tools available, the bulk of these tools being drawn from analysis. More recently, there has been considerable evidence that the way forward in these problems is considerably illuminated if, in addition to analysis, one uses differential topology. There have also been advances in the differential topology of dimensions 3 and 4, which have drawn extensively on physical sources, the principal source being Yang-Mills theories. Thus, there has been a genuinely two-sided interaction between the worlds of mathematics and mathematical physics. This book is intended as an informal introduction to some of these mathematical and physical ideas. It should be of use to graduate students and other research workers taking an interest in this material for the first time. So the differential topology, it kind of reflects, and just in the notion we were talking before, the preliminaries of the differential geometry, he assumes a topology, which is the usual simple topology of the open topology as of the usual course in topology, or its one-day introduction, if not a course, that there are other topologies. And so differential topology could assume that the topology goes from being a constant to a system. And so whereas otherwise just like a constant of integration or a constant of a value that can, in terms of being an invariant or fixed, that then it can be considered not a moving part, that it's introduced that differential topology would be something like the other moving part. So that similarly, an analogy for something like the nonlinear electromechanical effects on fields, we have the electric field, you got magnetic field, you got the kinetic field, you got the piezoelectric field, you got vibrations, and then you have also heat. So you have at least 3 levels of kinetic regimes, heat, vibrations, and displacement. And then as well you have electric and magnetic fields, and then as well you have stuff like light quantities, and as well all the superfluid and superconducting models and lack thereof, or insulating and trivially closed models and lack thereof, moving parts. So here, by looking at these differential equations, is kind of coming out of ODEs and PDEs and solving those, and then looking at how symmetries build them up for dynamical systems. Then differential geometry implements the idea, or begins to describe the submersions and immersions of these. It's called linearizations, and the linearization already has a term, and it's used in numerical methods. So I'll use it in this context, as I don't really use it otherwise very often. The meaning of methods of numerical methods that result approximations, although this is similarly not so different in at least some respects about its implicits and what it so defines. That I'll keep those two notions of linearization separate, the one for numerical methods and the one that only indicates this particular setting of a connectedness and that sort of thing. Because even though they might eventually have been written out or read off as these are the same kind of things, sleeve, that instead we might want to talk about those as differently later. So with the linearizations or immersions or submersions, immersions might be the best choice to pick for that we have something along the lines of symmetries, submersions, and then when we get into topology, if we could find another thing to do with S, symmetry, submersions, and sheaves maybe, or submanifolds. The idea would be to help identify what are the touchstones of the different things between these 3 applications in the fields, and whether they stack or whether they're distinct, and when their methods can be used together or not. That it results that we get talking about homeomorphisms and the diffeomorphisms, some algebraic topology, and we're just reading the contents of the topological preliminary that we get into homotopy groups, cohomology and homology groups, fiber bundles and fibrations, differentiable structures, manifolds. That gets into that topology has sheaves up in bundles, and sheaf cohomology is a thing. And he gets into index theory, which is reading off kind of like we talked about sequences and generators, and you got like index theory and sequences and generators. Algebraic varieties, Serre, S-E-R-R-E, Serre duality, line bundles, and Collar manifolds. Teichmüller space. Teichmüller space is when we were talking a little bit about the notions of degenerate arithmetic, which is itself just the parts of arithmetic that come together. So we might call it a primeval or arithmetic as a degenerate arithmetic, that these arithmetics might make it so that here's something like the Teichmüller space is kind of like the denormalized, renormalized space is after the point to the quantum to the continuous to the quantum to the point again. Teichmüller and everything after algebraic geometry is kind of similar, because arithmetic is, in a sense, degenerated by it. The dimension of the moduli space, Weierstrass gaps, and Weierstrass points. Then he talks about, in the theory of the chapter, some infinite dimensional groups, representations, the topology of critical points. The existence of critical points in topology is very much having to do with the continuous functions, and here with the immersions as well, that they must exist in every one of those neighborhoods about it. That's basically what the definition that topology provides, is that there's the nearness of the neighborhood of the points and as what's in them in terms of the uniform nature of those point sets with respect to surface or continuum. And then he talks about Morse theory, instantons and monopoles, and other physics-wise applications. So again, this is something now that we've looked at these books in the differential, and we have something like differential equations about symmetries, and after a very quick and brief and incomplete discussion about even just defining what is differential equations vis-a-vis real analysis, and that it's fundamentally computing the differential or the gradient and that kind of stuff, that we have topological quantum field theory, and then this contributions to nonlinear partial differential equations is kind of like when Stefani mentions the ansatz of the toolkit of the real analysts' solutions of differential equations. There's linear systems that have well-known and well-understood systems, and then there's methods of convolution. Methods of convolution and transform really offer at least a way to get also a foothold to numerical methods for chiseling out some kind of solutions to any equation. Then we talked about the computer algebra systems, which have codified a lot of this thinking, which goes into what makes that you plug in an equation and it gives you solutions. That it's as following this process. That here, this is an example from these contributions, that each one of these items here in this series is basically a solution or a description of a setting from dynamical methods. This is all from the world of dynamical methods. That is the whole milieu of real analysis and the applied. That cataloging all these methods and finding the suitable ones and finding where they have hidden assumptions, or otherwise finding where they have particular suitabilities and that kind of stuff, goes a long ways to helping to establish what would be the needful for a grab bag kit of a 2 or 3 page sheet that has a very simple breakdown of words and descriptions for definitions of systems of arithmetic and algebra, operator calculus, the properties of their algebras, the existence of their higher order algebras, the objects of analysis, then the regions, the realms, the domains, and these kinds of things, that then there would be for making a vocabulary and a glossary and common definitions for all what follows as a unified approach to dynamical differentiation, or this kind of a subset of a superset of a field. That then we have gotten so far into talking about the submersions and the symmetries and the sheaves with regards to the topologies and the algebraic varieties and the geometric varieties. Correspondingly, if to be correspondingly, that here what we're looking at are the fields is after arithmetic and after algebra and after invariant theory and symmetry theory and that, and after differential geometry, meaning as treated as up after a given topological setting, and what results for these submersions and those algebraic treatments of geometry, and this differential topology, where we'd get into measure theory and invariant theory again, and quasi-invariant theory, and when you have topological congruence of a sort. And then when we get into these higher level applications of more involved systems with the particulars, that gets into a pretty good thing. Well, that's a brief overview of talking about the differential analysis today and how to try and figure out how to make sense of a very big field with what would need to be some kind of putting together of all sorts of definitions from what are all sorts of very widely explored but various fields, and then how to figure out how to get a vocabulary and what are working terms that are good in all of the fields, that as well reflect all the moving parts necessary and result having together 3 toolboxes, and of those, 1 toolbox, where it's possible then to get things in and out of one set of tooling and in and out of another setting of a tooling, to work out for these ansets, then to make it possible for something like a computer algebra system, that then the computer algebra system writes out in these terms what it does in terms of plugging and crunching and getting an answer, and deconstructing and outlining and showing the answer. All right then. Hey, have a great day.